Okay, I want you to picture a wetland. Maybe it's, that mucky, quiet marsh you've driven past sometime, or maybe a dense, damp bog somewhere. Often these places are just overlooked, right? Sometimes people even see them as unproductive, maybe a bit messy. But here's the twist, and it's a big one. These seemingly unassuming lands are actually, well, unsung superheroes for our planet's health, especially when we talk about climate. Today, we're taking a real deep dive into these vital ecosystems. We're exploring what happens when human activities transform them. We're going to unpack some pretty surprising insights about soil, organic carbon, nitrogen, and maybe most critically, greenhouse gas emissions. Our understanding here comes from a whole stack of global meta analyses and detailed field studies, basically, a treasure trove of data from all over the world. And our mission today is to cut through all that complexity. We want to arm you with the most important facts and, honestly, some surprising discoveries about how land use changes affect wetlands and, ultimately, our climate future. By the end of this, hopefully, you'll grasp this intricate dance between land management and the planet's carbon cycle in a way that really sticks with you.
Yeah, let's set the stage because the numbers involved here are, well, they're truly astounding. Wetlands, despite covering only a small fraction of the Earth's land surface, maybe 5% to 8%, are these colossal stores of carbon and nitrogen. Think about this. They account for approximately 30% of the total carbon stock in the world's soils.
30% from just 5 to 8% of the land.
Exactly. So you can think of them as immense natural banks just quietly holding onto vast amounts of these critical elements.
Okay, that's a massive percentage for such a small area. So these wet, often overlooked areas are actually huge carbon and nitrogen banks, kind of keeping our planet's climate in check. Given they hold so much, how resilient are they, like naturally, to disturbances? And what's changed maybe in recent decades that makes human activity so much more impactful?
That's a really crucial question. Historically, wetlands were pretty resilient. They adapted over millennia to changes. But the speed and the sheer scale of human-induced changes, now things like drainage, conversion for agriculture, development, it just far outpaces their natural capacity to adapt. And this leads to the stark picture we see in the data. A major global meta-analysis, synthesizing results from 64 study sites. It found that wetland cultivation across most conditions led to a significant decrease in soil organic carbon, or SOC, averaging a 26.3% reduction.
Wow, over a quarter lost.
Yeah, and it's not just carbon. This extends to nitrogen, too. Other research reveals that converting natural coastal, riparian, and peatland wetlands generally decreased mean soil carbon concentrations by 25.5% to 31.1%. And the stocks themselves, the total amount, by 3.6% to 30.6%.
Okay.
Nitrogen saw even steeper declines sometimes. Concentrations dropping by 21.2% to 51.2%, and stocks by 10.7% to 38.3%. These are really significant global shifts.
So if these are our planet's carbon and nitrogen banks, and we're seeing such widespread withdrawals, I mean, it paints a pretty grim picture. But here's where the story gets really fascinating. Because it's not always a simple narrative of loss, is it? We found some, well, surprising nuances in the data that kind of challenge that common assumption.
Exactly. While widespread loss is the norm, the research highlights specific crucial conditions where wetland cultivation might actually lead to an increase in soil organic carbon.
An increase, really?
Yeah, what's fascinating here is that one key finding relates to wetlands that were originally tidal or salt wetlands. If these specific types were cultivated, and crucially, their initial SOC content was less than 30 grams per kilogram, so they weren't super carbon-rich to begin with, soil organic carbon actually increased by 33.8% and 30.6% respectively in those studies.
That's genuinely surprising. So let me get this straight. Coastal salt wetlands, if they start out low in carbon, could potentially benefit from cultivation in terms of storing more carbon. This kind of challenges the idea that disturbing wetlands is always bad. For someone listening, does this mean we should be, looking for these specific conditions, low carbon tidal wetlands for targeted restoration, or maybe even managed cultivation, understanding they're the exception?
Potentially, yes. I mean, it suggests a more nuanced approach is needed. It's definitely not a blank check for development everywhere, but it does indicate that with specific data-driven understanding of the wetland's original state and its carbon levels, certain actions might lead to positive outcomes, or at least less negative ones. Another factor is time. This is interesting, too. For wetlands cultivated for a very long duration, we're talking over 80 years, a positive effect on SOC was observed. Increases averaged 24.5% compared to control wetlands in those cases.
80 years, okay.
And climate conditions also play a role. Areas with a mean annual temperature between 15 and 20 degrees Celsius, or mean annual precipitation between 800 and 1,200 millimeters.
Yeah.
They showed a positive effect on SOC sometimes. Though admittedly, these climate links weren't always statistically significant, so they probably warrant more investigation.
Right. So it really seems like understanding the original state of the wetland, its type, its starting carbon level, plus the duration of human activity, and even the local climate. All these are critical for predicting the carbon outcome. It's definitely not a one-size-fits-all situation, which makes management much more complex, right? It demands a deep understanding of each unique ecosystem. Okay, so we've identified that converting wetlands often means losing vast amounts of carbon and nitrogen, but in some very specific cases, we might even see an increase. But the story doesn't end there, does it? Because what if the carbon we are storing isn't as robust as we think? This brings us to a crucial distinction. Not just the quantity, but the stability of that carbon.
That's a really critical distinction, yeah.
Yeah.
There was a study focusing specifically on how different vegetation types influence soil organic carbon. And it found that while certain forested wetlands, like those planted with willow and poplar, significantly increased total SOC compared to natural lakes edge and reed wetlands over 30 years, the stability of that accumulated carbon was sometimes lower.
Lower stability.
Yeah, meaning the newly stored carbon was more labily, or simply put, easily decomposable. It wasn't as securely locked away for the long haul.
Wait, so hold on. We might end up with more carbon overall, but it's less secure, more vulnerable to being released back into the atmosphere.
Yeah.
That's a twist. So the picture isn't just about total volume, but also about the integrity of that carbon store. Does this suggest we need different carbon accounting methods for wetlands, ones that consider not just volume but also durability? What happens if we only focus on quantity?
Precisely. If we're only counting the total amount, we might miss this critical nuance. It could be misleading. What happens is the higher net primary production, or NPP basically, faster plant growth in these forested wetlands leads to more fresh organic carbon inputs, lots of new material. And this fresh input, surprisingly, can even prime the existing older SOC to break down more quickly. It essentially helps release its carbon back into the atmosphere.
Wow, like adding kindling to a fire?
Kind of, yeah.
Yeah.
It helps the older, more stable logs burn faster, in a sense. It speeds up the replacement of that securely stored old carbon with new, more labile or easily decomposable carbon. So yes, it absolutely suggests a need for more sophisticated carbon accounting. We need to look at quality, not just quantity. However, there's a positive note here too. Among the forested wetlands studied, willow stands actually showed a higher SOC stability compared to poplar stands.
Oh, okay.
So if afforestation is a strategy being considered for a wetland area, the type of tree chosen matters significantly for long-term, stable carbon sequestration.
It seems like we're constantly uncovering layers of complexity. First, how much carbon, then how long it stays stored. But these land use changes don't just affect the ground beneath our feet, right? They have this dramatic and immediate ripple effect on the air above us, directly influencing the greenhouse gases that shape our climate.
Indeed, that's a major part of the story. Natural wetlands typically function as greenhouse gas sinks, or they're at least neutral.
Oh.
So they either absorb these gases or don't really contribute significantly to their release. However, converting them to other land use types fundamentally alters this balance. It drastically increases emissions of CO2, methane, CH4, and nitrous oxide, N2O. And this significantly boosts their overall global warming potential, or GWP.
The GWP, right.
Which means they shift from being allies in mitigating climate change to becoming active contributors to it. For a really striking example, the conversion of natural coastal wetlands to either cropland or aquaculture ponds increased their overall GWP by 7.8 to 29.5 times on average.
29.5 times, almost 30 times. That is a massive shift in their environmental role. How can we help listeners picture that? What's a relatable analogy? Is that like taking, I don't know, X number of cars off the road, or maybe adding a small city's emissions? How does that scale impact our climate goals?
It's a huge impact. While exact analogies are tricky because they vary by region and the size of the area, a nearly 30-fold increase in global warming potential for an area of converted wetland means that even a relatively small patch of land can suddenly have a disproportionately large climate footprint. It's maybe akin to turning a small, quiet park into a major industrial zone, just purely in terms of its emissions profile.
Okay, that paints a picture.
It significantly undermines efforts to reduce overall greenhouse gas concentrations. It makes our climate goals much harder to achieve, especially because these aren't one-off emissions. They're ongoing, sustained emissions once that conversion happens. And this specific type of land use change truly dictates the impact. Let's maybe break down some of the specific scenarios the research looked at.
Yeah, good idea.
Okay, first, agricultural lands, croplands. These conversions generally increase CO2 and N2O emissions, while actually decreasing methane sometimes. This is primarily due to things like drainage, tillage, fertilization, practices which shift the soil environment from anaerobic, meaning without oxygen, where microbes might produce methane, to aerobic, rich in oxygen. This oxygen fundamentally changes how organic matter decomposes. It speeds up the breakdown, releasing CO2, and it also stimulates the production of nitrous oxide, N2O, which is a much, much more potent greenhouse gas than CO2 over the long term.
Right, so drying it out and working the soil really changes the gas output.
Exactly. Think of a dry, tilled fields versus a soggy, untouched marsh. Very different chemical environments. Second, aquaculture ponds. Okay, these emerged as a major hotspot for GHG emissions, especially methane. Remember that GWP figure. For aquaculture ponds, it was found to be 29.5 times higher than natural coastal wetlands.
The highest figure you mentioned.
Yes. And this is largely due to the long-term waterlogging, the lack of natural vegetation, and then the buildup of organic matter from things like uneaten fish feed and animal waste. All that creates these perfect anaerobic conditions for methane-producing microbes to thrive. Imagine a shrimp farm at what used to be a mangrove forest that basically becomes a methane factory.
Got it. Waterlogged, lots of organic input, no plants, prime methane conditions.
Precisely. Then you have drained wetlands. Pretty self-explanatory, but as the name suggests, these conversions, whether they're in riparian wetlands near rivers or in peatlands,
Yeah.
they lead to significant CO2 emissions and also increases in N2O. Lowering the water table just exposes all that previously waterlogged organic matter to oxygen, stimulating that aerobic decomposition we talked about.
Okay, makes sense.
Pastures, next. Similar to croplands, converting wetlands to pastures generally leads to increased CO2 and N2O emissions. And in peatlands specifically, conversion to pastures was also found to significantly increase methane emissions compared to the natural peatlands.
So pastures aren't necessarily a gentler conversion in terms of GHGs, especially in peatlands.
Not necessarily, no, especially regarding methane in peatlands. But finally, constructed wetlands. Now, interestingly, these showed the most promise in the studies we looked at. While there were sometimes initial GHG increases observed, their soil carbon and nitrogen storage capacities actually had the potential to become similar to natural wetlands over time, especially when management focuses on restoration activities, things like revegetation, getting the hydrology right, adjusting the water levels. In fact, some coastal constructed wetlands were even found to increase net CO2 uptake eventually.
Okay, so constructed wetlands, if managed properly for restoration, could actually become part of the solution, not just less of the problem. That's hopeful. It's really clear, though, that not all conversions are created equal, and some, like aquaculture, are particularly problematic for greenhouse gas emissions, turning these vital sinks into major sources. The specific human choices really make a huge difference.
Absolutely. And what drives these changes fundamentally are shifts in the wetland environment itself. Changes in factors like the water table depth, the soil water content, pH levels, even the soil bulk density, how compacted it is. These are absolutely critical. Drainage, for example, directly lowers the water table and soil water content. That then promotes the aerobic decomposition, leading to the loss of carbon and nitrogen. It's like a chain reaction. One physical change triggers a cascade of biogeochemical effects.
Right, the physical changes drive the chemical and biological.
Exactly. And time. Time is a relentless factor here, too. The age of the conversion matters significantly. During the initial period, say roughly the first 0 to 30 years after conversion, we might actually see temporary increases in carbon and nitrogen stocks.
Increases, but
Yeah.
how?
Well, it can be misleading. It's often due to soil compaction from agricultural practices. Think heavy machinery, tilling. It essentially squeezes the soil particles together, like packing down a box. This increases its bulk density, so it temporarily seems like there's more carbon per unit volume.
Ah, an artifact of the density change, not necessarily more total carbon being stored long term.
Precisely. Because long-term observation, looking beyond 30 years, typically reveals a continued decline in the actual carbon and nitrogen concentrations. This is due to those sustained decomposition processes eventually outpacing any new inputs of organic matter.
That's a powerful analogy you used earlier. Like a house built quickly might look okay at first, but without solid foundations, it won't stand the test of time. It really highlights how carefully we need to manage these transitions, understanding that those apparent short-term gains might hide long-term, maybe even irreversible, losses. It's a classic ecological dilemma playing out right in our carbon budgets.
It really is.
Yeah.
And the implications for how we manage land are, well, profound. These findings truly underscore that sustainable land management strategies with a really strong emphasis on wetland conservation aren't just, good practice. They're absolutely crucial for mitigating climate change. We have clear evidence now that these land use changes turn wetland ecosystems into significant anthropogenic sources of greenhouse gases, directly enhancing the greenhouse effect.
So conservation first where possible.
Ideally, yes. But when wetland conversion is deemed necessary for other reasons, understanding the specific wetland type and its initial conditions, like we discussed with those tidal or salt wetlands that start with low initial soil organic carbon, that knowledge can inform practices designed to minimize carbon loss, or perhaps even promote sequestration in those specific cases. And things like rewetting. It's a common and often effective practice, especially in constructed or restored wetlands, to help bring back carbon and nitrogen storage and reduce GHG emissions. But it's important to note, full restoration can take a considerable amount of time, sometimes more than 15 to 50 years, and it requires sustained effort and monitoring. It's not a quick fix.
No quick fixes. This deep dive really emphasizes the need for extremely careful planning, robust monitoring, not just of the quantity, but also, crucially, the stability of carbon in these precious ecosystems. It truly personalizes the challenge, I think. It makes us think about the direct consequences of our land use choices on these often unseen natural systems and the significant ripple effect on our shared climate. So, as you consider the hidden power of wetlands and the really nuanced conditions that dictate their climate role, sometimes surprising conditions, maybe ask yourself this: what other natural carbon banks might we be unknowingly eroding elsewhere? And what specific, perhaps unexpected, nuanced conditions could, surprisingly, turn them into powerful allies for climate action, much like some of these wetlands under the right circumstances?